Cosmology has changed forever with the launch of James Webb on Christmas Day 2021. Ever since it opened its impressively sharp, high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathered sharp, pristine, and beautiful insights of early star and galaxy formation, and provided insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise: a bunch of the impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe. Our best cosmic predictions, based on lambda-cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake their understanding of galactic history. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and proto-galaxies, and these should be extremely blue and primitive, and again should only exist in low number densities the farther back we go. And finally, there should truly be a time where the very first stars and star clusters of all appear, and beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model, and to see if we truly understand the universe we inhabit, or if, and how, we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's SEERS, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Michaela Bagley of the University of Texas, one of the leading SEERS researchers, the theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early. One particular galaxy jumped out of the SEERS data straight away. Maisie's galaxy, named after the daughter of Stephen Finkelstein, one of the researchers, is 13 billion years old, making it one of the oldest galaxies ever observed. And it is much brighter and much bluer than anyone predicted. As Bagley said, when we found Maisie's galaxy, the surprising part was How is it in the universe? It's exciting that this is the universe we live in. It's a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, which is equivalent to what human eyes can see. But as galaxies move further and further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. So Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Maisie's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us, but if we could see Maisie's galaxy today, it is much, much further away because in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift, and thus age, of Maisie's galaxy were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the Sears team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's Near-Infrared Spectrograph, or NIR-SPEC for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data, dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Maisie's galaxy. It appeared to be 11.4. This means Maisie's galaxy is technically seen more recently in the universe than initially estimated, by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. The James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Maisie's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabio Pacucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought previously. The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter?" says Sandro Ticella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies. But there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into two types: spirals, which are disk-like with arms of dust and gas, and ellipticals, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs. But under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. In an attempt to explain the impossible massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They pushed the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidences at hand. So, up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, were shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. As Bagley explained, if the universe is smaller, the density inside galaxies and outside galaxies is probably higher. If it's dense and hot, the gas won't collapse to form stars. If it's dense and cold, then you could get a ton more stars. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe, because these elements were primarily formed within stars and spread by their explosive deaths, called supernovae. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. They were much bigger, heavier, and bluer than stars today, and they gave off more ionizing radiation. Those differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion, the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen, Bagley explained. There's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. but scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe, and telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today, and as the James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which Bagley refers to as baby pictures of the Milky Way. This is all about understanding how our Milky Way formed. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. In addition, on the hunt for alien civilization, NASA has just revealed that 17 discovered exoplanets could house subsurface oceans buried below thick sheets of ice. These worlds, much like the icy moons of Jupiter, could therefore be promising places to search for biosignatures, chemical signs of life. While the exact composition of these worlds remains unclear, estimates of their surface temperatures from previous studies point them being significantly colder than Earth. They're also each less dense than Earth, despite being roughly the same size as our planet. As Lynn A. Quick of NASA's Goddard Space Flight Center said in a statement, "Our analyses predict that these 17 worlds may have ice-covered surfaces but receive enough internal heating from the decay of radioactive elements and tidal forces from their host stars to maintain internal oceans." In other words, while their host stars may not provide conditions warm enough to keep water in liquid form on their surfaces, these planets may exhibit processes that can generate heat below their surface. The stretching and compression of rock inside a planet as it gravitationally interacts with its sun, for instance, could provide significant amounts of internal heat, enough to sustain a subsurface ocean. The radioactive decay of heavy elements inside the core of a planet can provide intrinsic heat as well. Thanks to the amount of internal heating they experience, all planets in our study could also exhibit cryovolcanic eruptions in the form of geyser-like plumes. Quick said, cryovolcanism meaning, in short, ice volcanoes. The study drew on what we know from the geyser activity of two of Jupiter's moons, Europa and Enceladus. Two of the exoplanets named in the research, Proxima Centauri b and LHS 1140b, were particularly promising candidates for having oceans relatively near the surface. Since our models predict that oceans could be found relatively close to the surfaces of Proxima Centauri b and LHS 1140b, and their rate of geyser activity could exceed Europa's by hundreds to thousands of times, telescopes are most likely to detect geological activity on these planets, said Quick. Follow-up observations of these worlds will likely include astronomers capturing the emission spectra of light traveling through these planets' atmospheres. Chemicals and molecules erupted into the atmosphere from cryovolcanic activity may hold clues as to whether life might exist in the cold, dark depths of these worlds. In a one-of-a-kind event, scientists just announced that Mars's atmosphere, once as thick as if not thicker than Earth's today, is leaking into space. About 0.11 cubic of Mars' atmosphere is pushed away every second by the incessant solar wind, the speedy stream of charged particles routinely blasted from the sun, which pervade the solar system and even reach beyond Pluto. But for a rare 2 days last December, some of that wind went away. Its sudden and dramatic disappearance caused the atmosphere on Mars's sun-facing side to swell by nearly 4 times its usual size, from its usual 800 kilometers to over 3,000 kilometers. The peculiar event was recorded by a NASA orbiter named MAVEN, short for Mars Atmosphere and Volatile Evolution, which has been observing both Mars's atmosphere and its response to the Sun's behavior since 2014. MAVEN's data showed other aspects of the Martian system, including the teardrop-shaped magnetosphere, the bow shock, and the ionosphere, expanded similarly. As Jasper Halikas, a professor of physics and astronomy at the University of Iowa and a member of the MAVEN team, said, "We're really off the charts here. This is something that we haven't seen at Mars before with MAVEN." The atypical episode, the first in nearly a decade of MAVEN's career, occurred after a fast-moving region of a solar wind overtook its slower counterpart and swept up the latter's material, leaving behind a sparse region. The emptied storm reached Mars on D-Sector 25, 2022, giving scientists a thrilling front-row seat to watch the planet's atmosphere balloon out, the way it might have been if it were circling a less windy star. According to Halikas, who is leading a new study, this was a Christmas present for us. Nature set up this perfect science experiment. With MAVEN's data of the unexpected dynamics on Mars, Halikas and his colleagues studied how extreme solar events and their absence influence the planet's atmosphere, an insight valuable to understanding its evolution. The findings also have implications for our understanding of Earth-like planets outside our solar system and how they interact with their host stars, the team shared on Monday. We could look under the hood at what physics is going on, how the dynamics are working, and really get a sense of those details, said MAVEN team member Skylar Shaver of the Laboratory for Atmospheric and Space Physics in Boulder. 2 days after the almost vacant storm passed Mars, the atmosphere around the red planet settled down to its original state once again, but not before bouncing a little like a jiggling plate of jello. A similar storm struck Earth in 1999, when our planet's atmosphere grew to 5 times its normal size. But there aren't often orbiting spacecraft positioned as well as MAVEN is now to study such events, the new atlas reported. Shannon Curry, the principal investigator for the MAVEN mission, suspects events like this were common during Mars' early evolution 3 to 4 billion years ago, when our sun was more fiery than it is now and perhaps blasted out storms once a week or even every day. Such extreme events were likely responsible for parching the red planet, a world scientists presume once hosted liquid water and offered conditions friendly toward life. Extrapolating the latest MAVEN data to study Mars' evolution through time could shed light on how much its atmosphere eroded away and how fast the planet dried up, Curry said. Curry added events like this may occur multiple times in the next 2 years as the sun's activity climbs to its peak, expected to occur in July 2025, if not late next year. Last, as a piece of good news, the Hubble Space Telescope, following a string of setbacks concerning one of its directional instruments, has now resumed its job of capturing deep space images. NASA confirms that in a statement posted to the Hubble Space Telescope blog. The telescope's issues all began on November 19th, when one of the iconic observatory's 3 gyroscopes, a trio that live on from an original set of 6, began providing faulty readings. In general, gyroscopes are devices that use either circulating beams of light or rapidly spinning wheels to help scientists make sure an object is facing the direction they want it to face. Incorrect gyroscope readings on the Hubble telescope, as you might imagine, can therefore drastically affect science measurements. To image a specific spot in deep space with this Earth-orbiting telescope, you'd have to make sure it's actually facing that spot in deep space. Thus, Hubble entered safe mode on November 19th, something that's programmed to happen automatically when certain issues arise with the observatory. The team, however, was able to bring it back online the following day. But things weren't looking good shortly after, when gyro issues sent Hubble into yet another safe mode situation on November 21. The team brought Hubble back once more, shortly after that, only for the beloved telescope to retreat into its dark corner once again on November 23rd. That most recent safe mode entrance was slightly worrying as it persisted for longer than the previous two dips. It wasn't too worrying though because, first of all, this isn't the first time Hubble's gyros have raised issues leading to a shutdown. And secondly, maybe most importantly, the observatory can actually function with only one gyroscope. The team just uses 3 because it maximizes efficiency. Though it's been over 3 decades since Hubble began exploring the vibrant reaches of our universe, and though a new observatory in town has been catching most of the spotlight recently, this Reynolds Wrap-looking telescope is surely not finished yet. The James Webb Telescope is a giant leap in the history of stargazing. With its advanced capabilities, including its ability to peer back in time to the very first galaxies that formed after the Big Bang, the Supreme Observatory is expected to shed light on fundamental questions about the origins and evolution of the cosmos. However, more than 2 years after operation, the telescope, albeit solved a lot of puzzles, is raising big questions about the early universe. The data obtained by James Webb isn't just quite what scientists expected. So, though dazzled by Webb's stunning images of deep space, scientists had to admit that something was amiss. What the telescope has revealed contradicts scientists' current theory of how the universe grew up, and it's beginning to look as if we may need to rewrite the history of the cosmos and reshape humanity's position within it. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. The James Webb Space Telescope, as you know, is one of the most advanced telescopes ever built. Planning for James Webb began over 25 years ago, and construction efforts spanned over a decade. It was launched into space on December 25, 2021, and within a month arrived at its final destination, 930,000 miles away from Earth. Its location in space allows it a relatively unobstructed view of the universe. The telescope design was a global effort, led by NASA, and intended to push the boundaries of astronomical observation with revolutionary engineering. Its mirror is massive, about 6.5 meters in diameter. That's nearly 3 times the size of the Hubble Space Telescope, which launched in 1990 and is still working today. It's a telescope's mirror that allows it to collect light. Webb's is so big that it can see the faintest and farthest galaxies and stars in the universe. Its state-of-the-art instruments can reveal information about the composition, temperature, and motion of these distant cosmic objects. Thus, for thousands of space scientists, the James Webb Space Telescope is a window to that unknown universe. Just how far back can James Webb peer into the cosmos and into the past? Well, about 13.5 billion years. A telescope does not show stars, galaxies, and exoplanets as they are right now. Instead, astronomers are catching a glimpse of how they were in the past. It takes time for light to travel across space and reach our telescopes. In essence, that means a look into space is also a trip back in time. This is even true for objects that are quite close to us. The light you see from the sun left it about 8 minutes, 20 seconds earlier. That's how long it takes for the sun's light to travel to Earth. You can easily do the math on this. All light, whether sunlight, a flashlight, or a light bulb in your house, travels at almost 300,000 kilometers per second. That's just over 18 million kilometers per minute. The sun is about 150 million kilometers from Earth. That comes out to about 8 minutes, 20 seconds. But the farther away something is, the longer its light takes to reach us. That's why the light we see from Proxima Centauri, the closest star to us aside from our sun, is 4 years old. That is, it's approximately 40 trillion kilometers away from Earth, so that light takes just over 4 years to reach us. Or, as scientists like to say, 4 light years. Most recently, James Webb observed Earendel, one of the farthest stars ever detected. The light that the telescope sees from Earendel is about 12.9 billion years old. The Webb Space Telescope is looking much farther back in time than previously possible with other telescopes, such as the Hubble Space Telescope. For example, although Hubble can see objects 60,000 times fainter than the human eye is able, the Supreme Observatory can see objects almost 9 times fainter than even Hubble can. But is it possible to see back to the beginning of time? The Big Bang is a term used to define the beginning of our universe as we know it. Scientists believe it occurred about 13.8 billion years ago. It is the most widely accepted theory among physicists to explain the history of our universe. The name is a bit misleading, however, because it suggests that some sort of explosion, like fireworks, created the universe. The Big Bang more closely represents the appearance of rapidly expanding space everywhere in the universe. The environment immediately after the Big Bang was similar to a cosmic fog that covered the universe, making it hard for light to travel beyond it. Eventually, galaxies, stars, and planets started to grow. That's why this era in the universe is called the Cosmic Dark Ages. As the universe continued to expand, the cosmic fog began to rise, and light was eventually able to travel freely through space. In fact, a few satellites have observed the light left by the Big Bang, about 380,000 years after it occurred. These telescopes were built to detect the splotchy leftover glow from the Big Bang, whose light can be tracked in the microwave band. However, even 380,000 years after the Big Bang, there were no stars and galaxies. The universe was still a very dark place. The cosmic dark ages wouldn't end until a few 100 million years later, when the first stars and galaxies began to form. The James Webb Space Telescope was not designed to observe as far back as the Big Bang, but instead to see the period when the first objects in the universe began to form and emit light. Before this time period, there is little light for the James Webb Space Telescope to observe, given the conditions of the early universe and the lack of galaxies and stars. Peering back to the time period close to the Big Bang is not simply a matter of having a larger mirror. Astronomers have already done it using other satellites that observe microwave emission from very soon after the Big Bang. So the James Webb Space Telescope observing the universe a few 100 million years after the Big Bang isn't a limitation of the telescope. Rather, that's actually the telescope's mission. It's a reflection of where in the universe we expect the first light from stars and galaxies to emerge. By studying ancient galaxies, scientists hope to understand the unique conditions of the early universe and gain insight into the processes that helped them flourish. That includes the evolution of supermassive black holes, the life cycle of stars, and what exoplanets, worlds beyond our solar system, are made of. However, data obtained by James Webb isn't quite what scientists expected. In the 2024 Isaac Asimov Memorial Debate, astrophysicist and science communicator Neil deGrasse Tyson moderated a discussion at the American Museum of Natural History in New York. The conversation was between scientists and surrounded the topic of how data from the telescope may be shifting our fundamental understanding of our universe. From discrepancies in the age of the universe to the unexpected brightness of early galaxies, the James Webb Space Telescope has already prompted scientists to reconsider how the early universe once operated, leading to revelations that could trigger major shifts in our models of the universe during the next decade or more of James Webb's tenure. And in the words of panelist Mike Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, the data from the telescope paints a consistent and consistently new picture of the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies. Far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe. and they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, the current story of the universe doesn't predict nearly enough dark matter, halos in the early universe, as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget, there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. What's notable, the impossible early galaxies aren't even the only things that keep cosmologists up at night. The Webb telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary, the trailblazing observatory found, further ratcheting up the so-called Hubble tension. Putting it simply, measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone such as Cepheid variable stars and Type 1 supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is, this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. The 5 galaxies observed by James Webb, the most distant of which is NGC 5468, at 130 million light-years from us, have also hosted a combined total of 8 Type Ia supernovas over recent decades. These supernovas, which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, Webb's observations of Cepheid variables therefore makes the distance measurements using Type 1 a supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. In the words of Rees, we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains is the real and exciting possibility we have misunderstood the universe. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. In other words, the tension at the heart of cosmology is here to stay. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. After all, there is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It is up to us to coax those secrets from its grip, transforming them from mystery into discovery. In a recent remarkable finding, James Webb has discovered that early universe galaxies must have grown up way faster than expected. Plus, the same team also found that 10 billion years ago, the cosmos wasn't quite as disordered and chaotic as previously believed. The international team, led by researchers from Durham University in the UK, reached these conclusions by discovering evidence of structures called star bars forming in galaxies that existed just a few billion years after the Big Bang. Star bars are elongated regions of increased star density found at the hearts of spiral galaxies like the Milky Way and other disk galaxies. As they form, star bars push gas toward the hearts of their respective galaxies, thereby regulating starbirth. The presence of these central bar structures thus indicate that a galaxy has entered a more settled and mature phase. As Zoe Leconte, team leader and a researcher at Durham University, said in a statement, "Galaxies in the early universe are maturing much faster than we thought. This is a real surprise because you would expect the universe at that stage to be very turbulent, with lots of collisions between galaxies and a lot of gas that hasn't yet transformed into stars. However, thanks to the James Webb Space Telescope, we are seeing a lot of these bars much earlier in the life of the universe, which means that galaxies were at a more settled stage in their evolution than previously thought. This means we will have to adjust our views on early galaxy evolution. Notably, this isn't the first time scientists have gone bar hopping in the early history of the 13.8 billion year history of the universe. The Hubble Space Telescope witnessed these features as well, but that orbiting eye on the universe could only go as far back as 8 billion to 9 billion years. However, the increased sensitivity and wavelength range of James Webb has stretched such observations back at least another 1 billion years. This has revealed bar formation in galaxies that are seen as they were between 8 billion and 11.5 billion years ago. In fact, of 368 disk galaxies the team considered for the study, 20% already had bars. That is double the number observed by Hubble. The further back in time the team looked with James Webb, the fewer bar structures they observed in galaxies. They believe this could be because galaxies at earlier stages of the universe were not as well formed. An alternative may be that shorter bars were more common in progressively earlier galaxies. Even the impressive observational power of James Webb isn't sufficient to see these short bars in early galaxies. With these results in hand, the team now wants to use the telescope to peer even further back into cosmic time, looking back as far as 12.2 billion years ago. This could reveal whether bar growth was common just 1.6 billion years after the Big Bang. As Goddard concluded, the simulations of the universe now need to be scrutinized to see if we get the same results as the observations we've made with the James Webb Space Telescope. We have to think outside of what we thought we knew. In another observation, the Webb telescope has discovered the oldest dead galaxy ever seen. But the cosmic corpse has left scientists puzzled as it defies explanation by our current knowledge of the early cosmos. The galaxy suddenly and mysteriously halted star formation when the universe was just 700 million years old, when countless stars were birthing thanks to an abundance of pristine gas and dust elsewhere in the universe. The galaxy, named JADES GS Z701QU, and described in a paper published in the journal Nature, provides astronomers with a peek into the elusive underpinnings of galaxy evolution in a primordial universe, including why galaxies stop forming new stars and whether forces driving their starbursts alter across epochs. In the words of study lead author Tobias Lusser, a researcher at the University of Cambridge's Kavli Institute for Cosmology, Cambridge or KICC, galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. Current models cannot explain how the newfound galaxy not only took shape in less than 1 billion years after the Big Bang, but also shut down its star factory so quickly. According to study co-author Francesco D'Eugenio, also a researcher at KICC, it's only later in the universe that we usually start to see galaxies stop forming stars. In comparison, a handful of other dead galaxies found elsewhere appear to have paused forming new stars when the universe was about 3 billion years old. To discover Jade's GS Z7 EWAOQ, Lucer and his colleagues used James Webb's powerful infrared vision to peer through the thick veil of dust obscuring the earliest objects in the universe. In addition to being the oldest dead or quenched galaxy spotted so far, the newfound galaxy is also many times lighter than other similarly quiescent galaxies previously found in the early universe. Webb's data suggest the galaxy intensely formed stars for somewhere between 30 million to 90 million years before it rapidly shut off, although precisely what ended it is still unknown. Astronomers know of a couple different factors that can slow down or extinguish star formation. For instance, turbulence inside a galaxy, such as radiation emitted by a supermassive black hole, can push gas out of the galaxy and starve it of the gas reservoir it relies on to form stars. Another intriguing possibility is that the galaxy's surroundings at the time did not sufficiently replenish the gas reservoir being consumed by birthing stars, leading to a deficit in star-forming material. However, in the words of study co-author Roberto Maiolino, an astrophysicist at KICC, we're not sure if any of those scenarios can explain what we've now seen with Webb. Current models based on the modern universe are unable to explain the properties of Jade's GS Z7901QU, suggesting they may need to be revisited. Another possible explanation for the new galaxy's dormancy could be that galaxies in the early universe die and then burst back to life. However, previous research of dead galaxies from when the universe was around 3 billion years old, a time of its most prolific star birth, suggested such dead galaxies cannot rejuvenate even via mergers with nearby galaxies, which instead only serve to puff them up. As Eugenio said, we'll need more observations to help us figure that out. A quick note, James Webb now is digging deep into the mysteries of gas planets. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The short answer is not very long, but the full story is far more nuanced. The research team used the Webb telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. According to Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, we knew that they exist and that they might play an important role in disk evolution. What we didn't know was the underlying physics, and consequently, how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. According to Bajaj, considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about 1 moon mass every year, it will take approximately 100,000 years. Yes, that sounds like a long time. But, as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. After all, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, James Webb should look.
out, it's so powerful, it might have just shattered our understanding of the universe.
Out in the depths of space, the James Webb Space Telescope is living up to its hype. From inexplicably bright galaxies to life on alien planets, and even the potential demise of our standard model of the universe, the most powerful telescope ever built has blown our minds with its stunning discoveries of multiple structures that shouldn't exist.
That's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how the shocking discoveries of James Webb could destroy the universe. To understand the dilemma, let's start by taking a quick look at the Big Bang, our best supported theory of our universe's origin. Originally, the Big Bang was a simple idea that grew out of three facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also, observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these three facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation, with a blackbody spectrum in all directions, arising from when the universe cooled through the threshold that enabled it to form neutral atoms. At even earlier times been hot and dense enough to initiate nuclear fusion reactions before any stars could form, leaving us with an initial abundance of elements other than hydrogen among the pristine set the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are three additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang, how hot and dense it was, what the initial spectrum of density imperfections were, including that we're all adiabatic, Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the standard model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time-evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continues to fuel doubts about the Big Bang theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy, GNZ11, at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 2 years after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 300 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 is now only the 11th most distant galaxy known. All 10 of the top 10 most distant objects were discovered and measured with James Webb. However, what's notable is that many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. Webb's finding then caused a stir in the astronomical world, with some scientists suggesting that it had put our current view of galaxy evolution, or even our understanding of the universe, into doubt. There weren't just inexplicably large ancient galaxies on James Webb's list of discoveries, but whopping black holes, too. The first, Sears 1019, had a mass 10 million times that of our Sun and was found by the James Webb Telescope just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. We say "at the time" because James Webb didn't rest on its laurels. Earlier this year, the telescope broke its own record again for the most distant black hole ever seen to date. The black hole dwells in the ancient galaxy GNZ11, which is 13.4 billion light-years away and is thus seen as it was just 400 million years after the Big Bang. The black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. And according to scientists, this discovery could be a giant step forward for black hole science, especially in understanding how supermassive black holes reached masses equivalent to millions of billions of times that of the Sun in the very early epochs of the universe. For decades, how these gigantic space-time ruptures swelled to such staggering scales so early on is an ongoing mystery. Astrophysicists are currently exploring options that include the black holes being formed from the rapid collapse of giant gas clouds, although they haven't ruled out that some may have been seeded by hypothesized primordial black holes, thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found more thousands of Milky Way lookalikes that shouldn't exist, swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgangers were found by James Webb more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. But Webb's finding revealed that the disk galaxies are 10 times more common in the early universe than astronomers previously thought. The strange discovery joins others made by James Webb that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. However, not stopped there, Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, the Webb telescope found 42 pairs of Jupiter-mass binary objects, or jumbios, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbos are too small to be stars, but as they bafflingly exist in pairs, they are unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets, or even for failed stars. While James Webb glimpsed deep space unlike ever before, it caused a stir in the whole scientific community as piercing through dust to find an ancient ghost. Look at this picture. It's a very blurry, highly dust-obscured resident of the cosmos, whose name is only a string of numbers and letters. It even sits at a distance so far from Earth that it slips in and out of the watchful eyes of various telescopes. The image, captured by the powerful James Webb Space Telescope, spotlights galaxy as TECC 71. But what's striking here is that we're seeing as TECC 71 the way it was just 900 million years after the Big Bang. That's when the universe was turning on its very first stars, absolute eons before our solar system was born. The Webb's view of this galaxy as a hazy speck of light is a far cry from many other glorious images of galaxies and galaxy clusters in its repertoire. However, even this smudge holds important lessons for our understanding of the early universe. Elsewhere, James Webb has helped set yet another record. Using the James Webb Space Telescope, astronomers have discovered star clusters in the cosmic gems arc that existed just 460 million years after the Big Bang. This marks the first discovery of star clusters in an infant galaxy, seen as it was when the 13.8 billion-year-old universe was less than 500 million years old. The cosmic gems arc, initially discovered by the Hubble Space Telescope and officially designated SPT 0615JD1, is a gravitationally lensed infant galaxy around 13.3 billion light-years from Earth. That means light from this galaxy, seen by James Webb, has been traveling to Earth for around 97% of the universe's lifetime. The international team of astronomers behind this discovery found 5 young, massive star clusters in the cosmic gems arc. These clusters existed during a period when young galaxies were undergoing intense bursts of star formation and emitting huge amounts of ultraviolet light. This radiation may be responsible for triggering one of 2 major phases in the evolution of the universe, the epoch of cosmic reionization. And when pointing Webb's sights on a star cluster about 1,000 light-years from Earth, astronomers discovered some unusual objects that is likely to be the least massive, free-floating brown dwarf that has been observed to date. In another remarkable observation, James Webb spotted a massive, gassy tendril composed of 10 closely packed galaxies stretching over 3 million light-years. According to the researchers, this ancient filament of gas and stars may represent the oldest known thread of the cosmic web. Another addition to the Webb telescope's long list of cosmic distance records was its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring, produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. How distant? A mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers to understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. Notably, while focusing to unlock the secrets of deep space, the James Webb Space Telescope also is revolutionizing our understanding of our closest cosmic neighbors. With its powerful infrared instruments, sharp spatial resolution, and exquisite sensitivity, Webb is forever changing our view of our celestial backyard. It is helping scientists answer important questions about our solar system, including how was the solar system formed and how has it changed over time? Where did the chemicals necessary for life on Earth, like water and carbon compounds, come from? What are the icy small bodies in the outer solar system made of? How are planets around other stars like planets in our solar system? Webb's extraordinarily sensitive spectroscopic instruments and state-of-the-art imaging capabilities enable analysis and mapping of solar system objects' atmospheres and surfaces. This is critical for studying planets, dwarf planets, moons, comets, asteroids, and ring systems. However, because Webb cannot point toward the Sun, it cannot observe objects between it and the Sun such as Mercury, Venus, Earth, or Earth's moon. Despite these challenges, exciting early results prove that it is possible to study planets with Webb. The telescope captured images and spectra of Mars, which allow scientists to study short-term phenomena like dust storms, weather patterns, seasonal changes, and, in a single observation, processes that occur at different times during a Martian day. In addition to finding the speedy Jovian jet stream described, Webb's view of Jupiter includes many fascinating details, including auroras, hazes, and tiny moons. In addition to finding carbon on the surface of Jupiter's moon Europa, that likely originated in its subsurface ocean. In the newest study, astronomers have used James Webb to find previously unseen structures and activity in Jupiter's atmosphere, above the Great Red Spot. These odd features seem to be caused by powerful atmospheric gravity waves. The Great Red Spot is the largest storm in the solar system, twice as big as Earth, and is believed to have been raging for at least 300 years. The winds of the Great Red Spot rage at around 430 to 680 kilometers per hour, up to 3.5 times as fast as a tornado here on Earth. But, despite the storm's age, size, and power, scientists had actually suspected that the atmosphere of Jupiter above the Great Red Spot wasn't all that interesting. However, these new observations delivered by James Webb's NIRSpec instrument, which observed the massive scarlet storm in July 2022, show that this assumption couldn't have been more wrong. After all, Jupiter never ceases to surprise. The telescope also detected a shockingly large water vapor plume spewing from Saturn's moon Enceladus. For the first time, Webb is giving scientists a direct look at how the water gushing from the surface of Enceladus, first detected by the Cassini spacecraft, feeds the entire system of Saturn, including its rings. Using Webb's infrared vision to study the atmosphere of Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, scientists detected clouds and observed airflow. For those who don't know, Titan is the only planetary body other than Earth that currently has rivers, lakes, and seas. However, unlike Earth, the liquid on Titan's surface is composed of hydrocarbons, including methane and ethane, not water. Put Titan aside, Webb's huge mirror and infrared sensitivity make it easier to see small, faint bodies such as Kuiper Belt objects, comets, asteroids, and centaurs. In the first demonstration of this capability, described in detail above, Webb captured the DART impact, NASA's inaugural attempt to move an asteroid in space. Webb enabled another long-sought scientific breakthrough, this time for solar system scientists studying the origins of Earth's abundant water. Using Webb's NIR-SPEC, or near-infrared spectrograph instrument, astronomers for the first time have confirmed gas, specifically water vapor, around a comet in the main asteroid belt. This indicates that water ice from the primordial solar system can be preserved in that region. However, the successful detection of water comes with a new puzzle. Unlike other comets, Comet 238P Reid had no detectable carbon dioxide. Scientists also used Webb to capture the shadows of starlight cast by the thin rings of Chariklo, a small icy body more than 2 billion miles beyond the orbit of Saturn. Only 250 kilometers, or 1,051 times smaller than Earth in diameter, Chariklo is the largest of the known Centaur population. Its rings orbit at a distance of about 400 kilometers from its center. Information gathered from these rings will allow astronomers to explore the ring's thickness, the sizes and colors of the ring particles, and more. Scientists hope to gain insight into why this small body even has rings at all, and perhaps detect new, fainter rings. Besides, remember that many different kinds of ice exist in the outer solar system, not just the familiar water ice. Other molecules besides water can form ices, such as nitrogen, methane, ammonia, and carbon dioxide. Webb excels in the study of ices in the solar system through the use of spectroscopy. Most often, it provides reflectance spectra, sunlight shining on an object and reflecting back, while the surface absorbs particular wavelengths of light. For ices in the outer solar system, it's not just the composition that matters, it's also the shape and structure. Different structures of ice, such as amorphous, crystalline, and irradiated, look different in spectra. The type can tell scientists about the temperature history of the object. In crystalline ice, the molecules are arranged in a highly regular pattern, forming lattices, such as in typical water ice on Earth. With amorphous ice, the molecules are irregularly grouped. In the cold, primordial gas between stars and across the universe, amorphous ice is the most common form. This is why Webb's integral field units are especially important. With a spectrum in every pixel, scientists can map out the surface of an object. One good example is Jupiter's moon Europa. By looking at a map of the carbon dioxide on Europa, we can tell that the carbon originated in the oceans because it is most abundant in a region where the terrain is quite new. Another example of the exquisite quality of Webb spectroscopy is the clear signature of crystalline ice revealed for the first time on Chariklo. Ground-based telescopes had hinted at this ice, but Webb saw the crystalline ice signature for the first time. Some of Webb's most intriguing discoveries involve searching for the building blocks of life beyond Earth. This search hinges on the accurate identification of chemical markers, such as water, carbon dioxide, and ammonia. These markers have strong infrared signatures that Webb can detect in the atmospheres and on the surfaces of planets, moons, and smaller bodies. And in a remarkable finding, James Webb has spotted the potential signs of life in alien farts on a Goldilocks water world 120 light-years away. The exoplanet it found, K2-18b, is a sub-Neptune planet, weighing in somewhere between the mass of Earth and Neptune, orbiting the habitable zone of a red dwarf star. After taking an atmospheric spectrum, the Supreme Space Observatory found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich Hycean world that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a cabbage-smelling compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more peeks at K2-18b and worlds like it to find further evidence for extraterrestrial life beyond our planet. Fascinatingly, the latest result of James Webb suggests an exoplanet is our best bet at finding an alien ocean. Dubbed LHS 1140b, the exoplanet orbits a red dwarf star about a fifth the size of the Sun and sits 48 light-years away from Earth in the constellation Cetus, which, as luck would have it, translates to the whale. But the most important about LHS 1140b is the fact that it lives in its star's habitable zone, otherwise known as its Goldilocks zone. As that nickname would suggest, this is the area around a star where it's neither too hot nor too cold for a world to host liquid water, but rather fits the standard by which the fairy tale character Goldilocks lives. There's also a second major win for the world. Though it has been making headlines now due to the new study involving Webb's data, LHS 1140b has actually been on planetary hunters' radars for some time. In fact, experts had already theorized that this could be a water world in the past, and even shared similar sentiments about how it could offer humanity the first ever direct evidence of exoplanetary liquid water. None of that is new. Scientists themselves have touted the world's promise previously, and an army of telescopes has investigated it in solid detail, including the now-retired Spitzer telescope, the Hubble Space Telescope, and the Transiting Exoplanet Survey Satellite, or TESS for short. However, there was something missing until now: the James Webb Space Telescope's keen eye. It was necessary because, for a long time, there was something like a gap in the literature about LHS 1140b. Basically, the trouble was that scientists couldn't quite confirm whether the exoplanet is a mini-Neptune, a planet less massive than our original Neptune, but one that still has Neptunian characteristics, or a super-Earth. A super-Earth is a world that's larger than Earth, but still either rocky or water-rich. The latter typically sounds the potential habitability alarm, and James Webb, scientists had imagined, could be the one to set it off. This appears to have been an accurate inference. As the team's statement on the study suggests, their work not only strongly excluded the mini-Neptune scenario, but also confirmed the world may have a nitrogen-laced atmosphere like Earth does. It is certainly worth noting that LHS 1140b isn't exactly fully alone in its exhilarating characteristics. There are also a variety of other habitable zone exoplanets scientists are drawn to. The most obvious are probably the 7 worlds of the TRAPPIST-1 system, a planetary lineup that looks almost disturbingly similar to our solar system structure. The septet of orbs resembles our octet, and some of them are in the habitable zone like Earth is. However, a very interesting Webb study actually complicated the search for habitability in TRAPPIST-1 quite recently. It revealed that the system's anchor star is incredibly active in such a way that it could skew our observations, making us believe a world in the system is habitable when it really isn't. Even James Webb has its limitations. So, to that end, LHS 1140b does have a few special embellishments. For example, data obtained by James Webb further suggests the exoplanet's mass might be made of between 10% and 20% liquid water. And it paints a fantastical picture of what the planet might look like in simple terms. It could look like a snowball, essentially, that orbits its star while rotating in such a way that one side always faces that star. It's kind of like the moon's orbit around Earth. We can't ever see the far side of the moon because the moon rotates at the same rate it revolves around Earth. One side never faces us, and the other always does. Similarly, this would mean that if James Webb's illustration of the LHS 1140b scene is correct, the side of the planet always facing its sun would be exposed to lots of heat. This would be the part of the snowball that's melted into a liquid ocean. And yes, if so, LHS 1140b has an Earth-like atmosphere, and its surface temperature of the ocean may very well even be a comfortable 20 degrees Celsius. And that is a very promising start. A previous study, the Webb telescope, revealed details of the mysterious gas giant exoplanet WASP-39b, which orbits a star about 700 light-years away from Earth. WASP-39b is tidally locked to that star, which means the same side of the planet always faces its star. In other words, half of the planet experiences perpetual day, and the other experiences perpetual night. But the dividing line isn't black and white. There's a proverbial gray area between the two halves that experience the equivalent of eternal dawn and eternal twilight, and it's in these areas that James Webb is revealing new information. Using those data, astronomers determined the temperature difference between these two transitional areas of the planet, a whopping 200 degrees Celsius. The morning is cooler at 600 degrees Celsius, while the evening is warmer at 800 degrees Celsius. What's more, models based on Webb's data also revealed weather patterns in these regions. For one thing, the dawn side is cloudier than the evening side. For another, the prevailing winds on WASP-39b appear to move from the night side, to the morning, to the day side, then to the evening, at speeds up to thousands of miles per hour. Astronomers will continue to dive into this data set to learn more about WASP-39b and other exoplanets. In addition, James Webb has mostly revealed insight into how everything began, but what about our eventual demise? Fear not, or maybe fear away, doom mongers. The James Webb Telescope had you covered this year with a spectacular light show from a dying star, a preview into the demise of our solar system. The donut-shaped ring nebula, also known as Messier 57 or M57, is a 2,200 light-years distant corpse of an exploded star, harboring at its center a tiny pinprick of a white dwarf that is the last remaining piece of the star's core. As it reached the end of its life, the star exploded outwards, hurling its innards far and wide to form what looks like a gigantic eye. The explosion likely obliterated or ejected any unfortunate planets in its way, a fate that will similarly befall our own solar system in 5 billion years' time. One of Webb's recent observations has found evidence of two giant asteroids slamming into each other in a nearby star system. The colossal collision ejected 100,000 times more dust than the impact that killed the dinosaurs. The violent impact occurred recently in Beta Pictoris, a star system located 63 light-years away in the constellation Pictoris. While the young star system currently contains at least 2 gas giant planets, it has no known rocky worlds like our own. But rocky inner planets may be in the process of forming thanks to large dust-producing collisions like the one spotted by James Webb, the researchers behind the new findings said in a presentation at the 244th meeting of the American Astronomical Society in Madison, Wisconsin. Because it is still very young, the star system's circumstellar debris disk, the vast ring of gas and dust surrounding the star, is a significantly more violent place than our own, making it the perfect place for astronomers to study the tumultuous early years of planet-forming systems. The team added that their findings could offer a rare insight into the history of our own solar system. And when it comes to hunting for the explosive deaths of massive stars in the early universe, James Webb is quite the cosmic detective. This celestial Sherlock Holmes has found evidence of 80 new early supernovas in a patch of sky as wide as a grain of rice held at arm's length. Not only is this 10 times more supernovas than have been uncovered before in such early cosmic history, but the sample also includes the earliest and furthest supernova ever seen. It's one that exploded when the 13.8 billion-year-old universe was just 1.8 billion years old. Data from the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES program, helped a team of scientists find this unprecedented clutch of supernovas, which further includes Type 1a blasts that astronomers call standard candles and can use to measure cosmic distances. Prior to James Webb's commencing operations in the summer of 2022, Only a handful of supernovas had been found dating back to when the universe was only 3.3 billion years old, equal to around 25% its current age. However, the JD sample contains many supernovas that exploded even further back in the past. In fact, some erupted when the universe was less than 2 billion years old. On the other hand, it is worth noting that while the James Webb's primary goal is to produce awesome science, and not just pretty pictures, sometimes the pretty pictures are the awesome science. Case in point, the stunning portrait of NGC 5068, a spiral galaxy sitting about 17 million light-years away. No ordinary galaxy, this one is spouting off new stars at a record pace. A team of astronomers was able to use multiple instruments on board the telescope to capture the galaxy in all its glory. After all, James Webb has beat all our expectations. What's more, the telescope is just taking its first steps into its journey to conquer the universe. Space engineers have calculated Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. In the next years, the telescope promises to deliver images of staggering beauty, while also providing scientists with data that has revolutionized our understanding of the cosmos. And that's really worth waiting. In the vast expanse of the cosmos, where mysteries abound and the unknown stretches endlessly, the James Webb Telescope, JWT, stands as a beacon of human curiosity and technological prowess. This groundbreaking instrument, heralded as the most advanced space observatory ever created, promises to unlock secrets of the universe that have long eluded us. But what if the very discoveries it makes are so extraordinary that they challenge the foundations of our understanding? Imagine peering into the early universe and finding not just the faint glimmers of ancient stars, but objects so bright and enigmatic that they defy current cosmological models. Nobel laureates and leading astronomers are sounding alarms, describing these findings as alarming and unsettling. The implications are profound, suggesting that the universe's infancy may not align with established theories and prompting a re-evaluation of everything we thought we knew about the cosmos. What exactly has the JWT uncovered? How could these seemingly innocuous spots of light challenge the very essence of our scientific theories? As we delve into these questions, we embark on a journey that not only pushes the boundaries of knowledge, but also reveals the ever-evolving nature of science. Join us as we explore the depths of these discoveries, the theories they confront, and the future they promise to unveil. Let's look back at the day the James Webb Space Telescope launched on Christmas Day 2021, and that day that inspiration was delivered. The James Webb Space Telescope was designed and developed by NASA engineers, along with the European and Canadian space agencies. It is the largest optical telescope ever sent into space, weighing in at 6 tons and costing $10 billion. On the morning of December 25, 2021, the Ariane 5 launch vehicle's rockets ignited, causing the ground in French Guiana to tremble. The roar signaled the start of the James Webb Space Telescope's JWST month-long journey to its current home, some 930,000 miles, 1.5 million kilometers, from Earth. Although it took scientists and engineers an additional 5 months to get the 6.5-meter telescope ready for action, the wait was worth it. In the 2 years since its launch, JWST has transformed our view of the universe. It was an achievement 2 decades in the making. But in just a short year since its launch, the James Webb Space Telescope has given scientists new perspectives, amazed the public with awe-inspiring images, and opened our eyes to the infinite possibilities of the universe. Click the follow button now. We're about to uncover an astonishing truth that scientists are calling alarming and concerning. Take a look at this image. This is a newly discovered early galaxy that existed about 13 billion years ago. But researchers found that this galaxy is much larger and more mature than expected for a galaxy in the early universe. This is not the first time that Webb has found such galaxies in the early universe. Since the Webb telescope began its journey, it has challenged our standard cosmological theories. This amazing telescope is not stopping there. This time, the telescope has revealed something disturbing about the universe. Recently, a Nobel Prize-winning scientist revealed that the James Webb telescope has finally confirmed that our understanding of the universe is completely wrong. Yes, it is not about large and bright galaxies, but this time, some new and more important observations from the James Webb telescope have shattered long-standing cosmological theories. Consider this. One of the pillars of cosmology is that the spatial distribution of matter in the universe is uniformly isotropic. That is, everything looks the same in every direction if you look over a large enough distance. This is obvious because the forces are expected to act equally across the universe on large scales and therefore do not create any observable inequalities in the large-scale structure during the evolution of the initial matter field created by the Big Bang. Wherever you look, you see the same density of matter, the same temperature, and the universe is expanding the same everywhere. For more than a century, scientists have developed various cosmological models that assume that our universe is uniform in all directions. The Big Bang model, which is the best theory for understanding the universe, is also based on this assumption. The cosmic microwave background radiation also shows that the universe is the same everywhere. But a new study published on February 6 in the astrophysical journal Letters suggests that there may be something really wrong with this assumption. Astronomers have recently confirmed that the rate of expansion of our universe is not the same everywhere in the cosmos. In this paper, they reveal that depending on where we look, the universe is expanding at different rates. Now, this is a big problem because if the universe is expanding at different rates in different places, it would create a big problem for astronomers. This new study also suggests that we may be completely wrong about our current estimates of the age and nature of the universe. We wouldn't call it a tension or a problem, but a crisis, says Nobel Prize-winning astronomer David Gross. Let's dive deeper into this discovery and see how the new Webb telescope discovery confirms a crisis in cosmology. In 1929, Edwin Hubble provided the first observational evidence that our universe is expanding everywhere. Using the largest telescope of the time, he discovered that the farther a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding equally in all directions. From this discovery, scientists thought that if the universe is expanding, then this expansion must have started at some point in the past, which means the universe must have a finite age. And since the expansion is happening equally everywhere, by precisely determining the rate of expansion, known as the Hubble constant, the cosmic clock can be rewinded and the age of the universe calculated. But before the Hubble telescope was launched, there was huge uncertainty about the rate at which the universe is expanding, or the Hubble constant, h0. This value is needed to calculate the age of the universe, estimate its evolution over billions of years, and understand the forces that drive it. When the Hubble Space Telescope was launched, it revealed that the universe could be as young as 9.7 billion years or as old as 19.5 billion years. But this younger value posed a big problem. It meant the universe was younger than the oldest known stars. Over the centuries, astronomers have used a variety of methods to measure the exact value of the expansion rate. But surprisingly, each method gives different values. It is as if the universe is expanding differently for different observations. Currently, there are two gold standard methods for finding the Hubble constant. The first method involves sifting through tiny fluctuations in the cosmic microwave background, an ancient relic of the universe's first light, created just 380,000 years after the Big Bang. Between 2009 and 2013, astronomers mapped this microwave blur using the European Space Agency's Planck satellite to infer a Hubble constant of about 67 kilometers per second, per megaparsec. In the second method, we use a Cepheid variable star or supernova as a distance source. As Cepheid stars get brighter, they pulsate more slowly, giving astronomers a way to measure their absolute brightness. By comparing this brightness to the observed brightness, we can calculate the rate at which the universe is expanding. But this is where the mystery begins. According to Cepheid variation measurements, the expansion rate of the universe is about 74 kilometers per second per megaparsec, an incredibly high value when compared to Planck's measurements. Initially, some scientists thought that this discrepancy might be the result of measurement error. But recently, Adam Rees, professor of physics and astronomy at Johns Hopkins University, said, "We have now covered the entire range that Hubble observes, and we can rule out measurement error as the cause of Hubble's stress with very high confidence." In addition, new images from the James Webb Space Telescope confirm that previous measurements are correct and that the universe is expanding differently in different places. This difference in the value of the expansion rate of the universe suggests that perhaps the universe is not the same everywhere. Well, if this is true, then our standard cosmological model falls apart because we cannot estimate the age and size of the universe using different values of the expansion rate. And the most important question that arises is, why is the universe expanding differently in different places? One interesting reason could be that dark energy, the mysterious force that seems to be driving the acceleration of the expansion of the universe, is itself not uniform. In other words, dark energy is stronger in some parts of the universe than in others, causing different expansion rates. Scientists claim that if the universe is not homogeneous and isotropic, it means that the laws of physics as we understand them are incomprehensible. Just above the cosmic horizon, gravity could work in reverse, the speed of light could be slower than walking speed, and unicorns could be real. This new discovery from the James Webb Telescope has sparked a major debate among astronomers. The reason is that the uneven expansion of the universe challenges the cosmological principle, which is one of the foundations of astronomy. What do you think about the above event? Subscribe to our channel and leave a comment below. We will discuss this issue together. Now, don't take your eyes off the screen. Join us as we explore the amazing things JWT has discovered over the past 2 years. Number 1. Unveiling the Crab Nebula. Within the constellation of Taurus lies the Crab Nebula, a canvas of cosmic activity captured here through Webb's NIRCam and MIRI. The compass on the image may seem inverted because we're used to maps of the Earth, but this is the sky map and we're looking up into it. The scale here is immense, defined by light years. A distance light travels in a year, about 588 trillion miles. The light we see in this image began its journey 6,500 years ago, traversing time and space to reach us. Across this stretch, the image covers 10 light years. At the core of the nebula is a pulsar, the remains of a supernova, spinning rapidly and flashing like a lighthouse. The Crab Nebula, or M1, is not just a remnant, but a birthplace for new elements that make up planets and life. In this 5.5 arc-minute wide snapshot, we're witnessing a part of the universe's continuous cycle of death and rebirth. Isn't it a marvel how destruction and creation are intertwined in the cosmos? Number 2. The Majesty of Max 0416. Gaze at the image of Max 0416, a galaxy cluster so massive that it bends light around it. This cluster has been captured by Hubble in visible light and by Webb's NIRCam and infrared, offering a dual perspective on the same celestial marvel. The compass arrows here might seem backward, but they're not. They simply reflect the sky's orientation from our ground-based point of view. The scale is measured in arc minutes, a sliver of the sky's vast canvas, with the entire image stretching just over 2 arc minutes wide. That's a tiny angle, but it represents an immense portion of the cosmos. Known formally as Max J046.12403, this cluster lies in the constellation Eridanus. It's a gravitational lens, warping space to magnify and distort the light of galaxies behind it. It's like looking through a cosmic magnifying glass, revealing galaxies that would otherwise remain hidden. Such clusters are not just fascinating subjects for images, they're also critical to our understanding of how mass is distributed across the universe. Through Max 0416, we peer deeper into the universe's mysteries. Number 3. Max 0416 and the marvelous Mothra. Venture into the cosmic depths and feast your eyes on Max 0416, a galaxy cluster with a special twist. This isn't just any cluster, it's a colossal cosmic magnifying glass, bending light across the eons to unveil a spectacular secret. A distant galaxy that flickered into existence a staggering 3 billion years after the Big Bang. And there's a standout star in this galactic ensemble, fondly named Mothra by the scientists, charmed by its brilliance. This isn't your ordinary star. Mothra shines with a light magnified over 4,000 times, a brilliant beacon that has traversed time and space to greet us. But what's the power behind Mothra's extraordinary glow? It's the combined might of Max 0416 and a mysterious lens, a dense celestial body with the mass of a swarm of stars known as a globular cluster. This discovery, nestled in the constellation Eridanus, is not just a testament to the wonders of the universe. It's also a thrilling clue in our cosmic detective story as we unravel the nature of the universe's hidden mass. Each glimmer in the vast dark is a story, and Mothra's is one of ancient light amplified across the ages, reaching us against all odds. What else might lie out there waiting to be magnified into view? The universe is full of such dramatic tales, and Max 0416 is just one chapter. Number 4. Webb's groundbreaking discovery, thorium from a star merger. In a celestial drama of epic proportions, Webb has struck scientific gold, or rather, thorium, detecting this rare element in the cosmos. In the grand tapestry of the universe, 2 neutron stars, remnants of stellar explosions, danced their gravitational tango in a distant galaxy before ultimately merging in a cataclysmic event. The prelude to this discovery began with 2 stars bound by gravity's inexorable pull within a spiral galaxy far beyond our own. Each star met its end in a supernova, leaving behind neutron stars, incredibly dense celestial objects. Propelled by their explosive births, these stars embarked on an intergalactic odyssey, finally colliding after several 100 million years. This violent merger set the stage for a spectacular cosmic light show, a gamma-ray burst, GRB 23307A, an explosion so powerful it shines with the light of 1,000 novas. GRB 23307A, first spotted by the Fermi Gamma Ray Space Telescope, stands out as the second most luminous gamma-ray burst we've ever seen. Webb's infrared capabilities allowed scientists to pinpoint the origin of these neutron stars and witness the aftermath of their merger. It's here that Webb spotted signs of thorium, an element scarcer than platinum on Earth, within the kilonova glow. This marks the first time such a heavy element has been directly observed in the aftermath of a neutron star collision. The significance? Kilonovas are now confirmed as cosmic forges, where the universe's heavier elements are crafted. Webb's detection of thorium is just the beginning. Astronomers are on the brink of uncovering more secrets of the cosmos, revealing the origins of elements that construct the world around us. This discovery not only enriches our understanding of the cosmic life cycle, but also hints at the untold treasures still hidden in the vast darkness, waiting for Webb to reveal them. Number 5. The distant beacon. Unveiling a primordial black hole. Astronomers have peered across the cosmic expanse to witness a black hole from the universe's dawn. Using the keen eyes of the Chandra and Webb space telescopes, this black hole, detected through its X-ray whispers, holds the record as the most distant one we've ever seen, shining from a galaxy known as UHZ-1. Such X-ray emissions are the hallmarks of a supermassive black hole feasting on surrounding material, growing larger with every bite. The black hole's story unfolds against the backdrop of the galaxy cluster Abell 2744, imaged here in infrared by the James Webb Space Telescope. This cluster, nicknamed the Pandora Cluster, is a cosmic crossroads, a gathering of galaxies whose light has traveled for billions of years to reach us. As we dive into Webb's infrared portrait, we find an ocean of darkness sprinkled with distant suns and galaxies. These dots of white, orange, and purple light are not just points, but entire galaxies, each with their own stories spiraling and stretching across the void. Among this cluster of galaxies lies an inconspicuous orange dot, seemingly modest, yet a beacon from the past, signaling from 13.2 billion light-years away. That speck houses a burgeoning supermassive black hole in the galaxy UHZ-1, a rare glimpse into the early life of such cosmic giants. This image is not just a photo, it's a window into the early universe, offering clues to how the first supermassive black holes emerged. It's a snapshot of a youthful universe, and within it, a black hole that's grown for billions of years since. It's a profound reminder of the vastness of the universe and the enduring mystery of its origins. Before JWST, astronomers thought galaxies began as small clouds of gas, dust, and stars that gradually grew into the island universes we see today. But the telescope's ability to see infrared radiation allows it to peer farther into space and thus further back in time to when galaxies first formed. JWST has found several of these youngsters that date to within 500 million years of the Big Bang, and they are much brighter than anyone expected. The galaxies could be more efficient at creating stars than predicted, churning out massive stars at a higher rate, or most intriguingly, more massive than astronomers believed possible. Scientists also have found more advanced structures in some spiral galaxies around cosmic noon, when the universe was 2 billion to 3 billion years old and making stars at their greatest rate. In addition to making amazing discoveries, JWST also combines with other telescopes to create stunning images, like this one of the Ghost Galaxy M74. Early supermassive black holes. Astronomers found the most distant black hole ever detected in X-rays in a galaxy dubbed UHZ-1 using the Chandra and Webb space telescopes. Everyone knows that black holes grow as they devour passing stars and clouds of gas and dust. So it comes as a surprise to find supermassive black holes, SMBHs, lurking in the early universe when they haven't had much time to chow on their surroundings. JWST has discovered several black holes, weighing about 1 billion solar masses dating to 800 million years after the Big Bang. Perhaps even more importantly, the telescope has turned up much smaller SMBHs with masses from 1 million to tens of millions of suns at even earlier times. This could provide astronomers with enough data to figure out how these behemoths evolve. Dust in the universe's youth. A young galaxy called JD's GS-Z6 was recently targeted with JWST. The powerful telescope noted possible traces of molecules not expected so early in cosmic time. Dust appears all around us, in fluffy bunnies lurking under our beds, in dark clouds blocking our view of the Milky Way, and as signatures in the spectra of distant galaxies. Most dust contains carbon, so it's a relative latecomer to the cosmos because early stars had to forge the element from their initial supplies of hydrogen and helium. Yet, JWST has found dust in a galaxy just 1 billion years after the Big Bang. The dust has a unique chemical fingerprint, suggesting it may be a mix of graphite or diamond-like grains created in the earliest stars. It opens a new window into dust production and galaxy formation. Studying star formation in detail. The Rho-Ophiuchi cloud complex, the closest star-forming region to Earth. Stars form in dense clouds of gas and dust. Unfortunately, dust blocks visible light, shielding much of the process from view. But the infrared radiation JWST sees penetrates dust, opening a new window into star birth. For example, it has revealed thousands of new stars buried deep within the Eagle Nebula, M16, that Hubble couldn't reach. And JWST also showed remarkable detail in a section of the nearby Rho-Ophiuchi complex. The telescope's images have revealed dozens of young, low-mass stars, as well as the jets they emit, which light up surrounding clouds of molecular hydrogen, a dusty supernova remnant. At left, supernova remnant Cassiopeia A, CAS-A, as captured by NASA's James Webb Space Telescope's NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. Just 340 years ago, light from an exploding star first reached Earth. Today, we see the supernova's remnant, known as Cassiopeia A, CAS-A, as a 10-light-year-wide debris shell. CAS-A's stunning beauty in the infrared comes from wispy tendrils of gas and the soft glow of warm dust. The dust intrigues astronomers because it is a basic building block of planets and life. They suspect most cosmic dust forms from the heavy elements supernova eject, though previous studies couldn't explain the amount of this material seen in early galaxies. Scientists hope JWST's observations of CAS-A and other supernova remnants can shed more light on its creation. A jumbo surprise. The jumbios, short for Jupiter mass binary objects, discovered by the JWST. Deep in the heart of the Orion Nebula, M42, lie at least 40 planet-sized objects with a binary companion. Dubbed jumbos, short for Jupiter mass binary objects, the bodies defy all expectations. Although many stars have companions, astronomers didn't think planetary mass objects could. No star formation theory can create objects this small, and if they develop in circumstellar disks like planets do, they shouldn't be able to survive a forceful ejection. Astronomers likely will need to revise their ideas about star or planet formation or come up with a new theory for creating these jumbos. A molecular exoplanet revolution. This artist's concept shows what exoplanet K2-18b could look like based on science data. It orbits the cool dwarf star K2-18 in the habitable zone and lies 120 light-years from Earth. Although images draw the most attention, spectroscopy plays a huge role in JWST's explorations. It allows astronomers to determine the redshift and thus distance of faraway galaxies, and to analyze the chemical composition of astronomical objects. Nowhere is this more important than in the study of exoplanet atmospheres, where JWST's infrared capabilities allow it to detect molecules invisible in optical light. Among its many discoveries, JWST has found methane, carbon dioxide, and dimethyl sulfide in K2-18b, a rocky world in its star's habitable zone, hinting that it could harbor a water ocean on its surface. Rings around the Ring Nebula. NASA's James Webb Space Telescope has observed the well-known Ring Nebula in unprecedented detail. The Ring Nebula, M57, in Lyra, ranks among the sky's most beautiful planetary nebulae, the end state of sun-like stars. JWST has revealed intricate details in the ring itself, which comprises some 20,000 clumps of molecular hydrogen. But what really sets M57 apart in JWST's images is a series of 10 concentric arcs beyond the main ring's outer edge. Astronomers think the arcs first formed near the dying star when ejected gas interacted with a low-mass companion that orbits at a distance about that between the Sun and Pluto. Diving into protoplanetary disks. These Webb images show a part of the Orion Nebula known as the Orion Bar. The largest image on the left is from Webb's NIRCam, near-infrared camera, instrument. At upper right, the telescope is focused on a smaller area using Webb's MIRI, mid-infrared instrument. At the very center of the MIRI area is a young star system with a protoplanetary disk named D203506. The pullout at the bottom right displays a combined NIRCam and MIRI image of this young system. Planets form in dusty, gaseous disks surrounding young stars. JWST observations not only have provided unprecedented detail in these protoplanetary disks, but also tantalizing clues of precursors to life. Around the nearby star Fomalhaut, the telescope found 3 nested belts of warm dust, suggesting that planets shaped the disk. The observatory also detected water vapor in the inner disk surrounding PDS 70, showing that any terrestrial planets forming there would have access to water. And in the protoplanetary disk surrounding the young star D203506 in the Orion Nebula, JWST discovered the methylcation, a molecule that likely plays a key role in interstellar organic chemistry and the genesis of life. The James Webb Space Telescope has made stunning discoveries, opening up new perspectives on the dark ages of the universe. The images and data captured not only reveal the farthest corners of space, but also the current understanding of the formation and evolution of galaxies and stars. The Nobel laureate has presented the terrifying truth about what the telescope has seen, and it is truly alarming. The existence of ancient cosmic objects, including supergiant universes and previously unknown angels, raises new questions about the origin and development of the universe. This is not only a great step forward for science, but also a reminder of the mysteries that await to be solved in the not-too-distant future. Deep in the outer reaches of the solar system, so far away from the known planets that the sun would barely be distinguishable from a nearby star, a massive, icy world may be lurking in the shadows, waiting to be discovered by humanity. Dubbed Planet 9, this hypothetical celestial body has been the subject of intense scientific debate and speculation since its existence was first proposed nearly a decade ago. Some researchers believe it might have been a rogue planet captured by our sun's gravity, while others think it could have formed from the same disk of gas and dust as the other planets. If Planet 9 exists, it is believed to be 10 times more massive than Earth and orbit the Sun at a distance of 400 to 800 astronomical units, which is 400 to 800 times the distance between the Earth and the Sun. Astronomers have been eagerly hunting for clues, using powerful telescopes and advanced computer models to track its influence. After years of watching the sky, solving mathematical equations, and running complex computer simulations, they now have the strongest evidence yet that Planet 9 really exists. This discovery introduces an exciting plot twist in the story of the hidden planet. Join us in today's episode as we dig deep into the enigmatic Planet 9, as well as compelling evidence supporting its presence. The Planet 9 hypothesis. The idea of a ninth planet in the solar system was first seeded by the discoveries of Uranus in 1781 and Neptune in 1846, more than 3,000 years after the other planets were first spotted by the Babylonians. These discoveries proved that the solar system was much larger than humanity had once thought and raised the possibility that other worlds were waiting to be discovered. But other than the now demoted Pluto, no full-fledged planets beyond Neptune or the Kuiper Belt, a massive ring of asteroids, comets, and dwarf planets that orbit the Sun beyond Neptune, have shown up since. And as astronomers mapped more of the outer solar system, it seemed increasingly unlikely that they were missing something as large as a planet. However, a 2004 discovery changed that. Scientists found that Sedna, a potential dwarf planet located beyond the Kuiper Belt, had a weird orbit around the Sun. Its unusual trajectory hinted that another large mass in the outer solar system was gravitationally pulling on the mini-world. But without more information, this hypothesis was hard to prove. Then, in a 2014 study, astronomers announced that they had detected a smaller object in the Kuiper Belt, named 2012 VP113, with an eccentric orbit similar to Sedna's. The findings also hinted that more eccentric trans-Neptunian objects, known as TNOs, were waiting to be found. These findings caught the attention of Mike Brown and fellow Caltech astronomer Konstantin Batygin, who noticed that both Sedna and 2012 VI P113 had the same kink in their orbits. This shared irregularity, which causes the objects to briefly dip below the known planet's plane of orbit, suggested that something, such as an asteroid clump, a dwarf planet, or even a full-fledged world, was tugging on these objects. But even after the pair realized a ninth planet was possible, they decided to sit on their findings until they could come up with another, less controversial explanation. However, they then found 4 more TNOs with matching misshaped orbits, which suddenly made a missing planet look like the most logical explanation. At the time, the duo calculated that there was just a 2% chance that all 6 TNOs they had studied shared their orbital oddities thanks to random chance. So, in 2016, Brown and Badigan published their Planet 9 hypothesis, which has captured the public's imagination ever since. The hunt for Planet 9. Since 2016, Brown, Badigan, and others have continued the hunt for Planet 9. Although they have not found it yet, they have discovered even more eccentric TNOs, bringing the total to 13 and further strengthening the case for Planet 9. These discoveries also constrain Planet 9's potential size, its distance from the Sun, and its orbital trajectory through the solar system. Our best estimates are that it's about 7 times more massive than Earth, or anywhere between 5 and 10 times the mass of our planet. This would make it the 5th most massive planet in the solar system, behind Jupiter, Saturn, Neptune, and Uranus. Planet 9's composition is probably most like Neptune due to its distance from the Sun. That would put its diameter at something like 2 times the width of Earth. Some scientists have also suggested Planet 9 could be surrounded by moons, just as the hefty gas giants are. If it exists, Planet 9 is likely around 500 astronomical units away from the Sun on average, meaning it's 500 times farther from the Sun than Earth is. This may sound distant, but similarly sized exoplanets have been discovered orbiting alien stars at equally massive distances, showing that this is possible. This far out, it could take between 5,000 and 10,000 years for Planet 9 to complete a single trip around the Sun. Its orbit is probably highly elliptical, so its distance from the Sun would vary widely over time. It also likely does not orbit on the same plane as the rest of the planets, which makes it even trickier to find. Planet 9's unusual orbit and extreme distance from the Sun also raise the possibility that it could be a rogue planet, an interstellar world that was captured by the Sun after being ejected from its star system. However, Brown and Badigan believe Planet 9 likely formed alongside the other planets in the solar system. Why haven't we found it? But if Planet 9 does exist, where is it? Why haven't we spotted it yet? The short answer made by scientists is that the hidden planet is very, very far away. Light reflected off the planet would be very dim by the time it traveled across most of the solar system twice, which makes it all but impossible to see. Initially, the researchers also had no idea where the planet was along its predicted orbital path. That means they've had to study a huge region of the sky to look for this faint body, akin to trying to find a single white whale in an ocean. So far, researchers have analyzed thousands of images from multiple sky surveys along Planet 9's proposed orbital pathway, looking for objects that move over time. Unfortunately, the night sky is teeming with bright moving objects, such as comets, so the researchers have to sort through a lot of garbage to find the planet. In their most recent work, Brown and Badigan analyzed data from the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, at Haleakala Observatory in Hawaii, and confidently ruled out around 78% of the suspected orbital pathway as possible hiding places for the planet. This narrowed down Planet 9's location to somewhere in the most distant 22% of its orbital pathway. Unfortunately, telescopes like PAN-STARRS are not powerful enough to properly search this space. When will we find it? That means if Planet 9 is hiding in the most distant reaches of its orbit, we'll need a telescope powerful enough to spot it. Brown and Battigan have already begun analyzing data from Japan's Subaru telescope in Hawaii, which has a better chance of finding the planet than Pan-STARRS does. But if this survey fails to complete the job, they will turn to the forthcoming Vera C. Rubin Observatory, which is currently under construction in Chile. This ground-based telescope, which will be equipped with the world's largest digital camera, will let researchers peer farther into the solar system than any of its predecessors allowed, similar to how the James Webb Space Telescope has enabled researchers to look farther across the observable universe than ever before. The observatory is currently slated to open in late 2025. With the help of the state-of-the-art telescope, Planet 9 could be found within the next 2 years. However, in the worst scenario, if the telescope cannot find the planet within the first few years, then the hypothesis is pretty much dead. But scientists also pointed out that even if the telescope does not find the planet immediately, it could still identify more TNOs, which would help show if the theory is viable. Why does Planet 9 matter? After all, while scientists remain divided over Planet 9's existence, one thing they all agree on is that actually finding the elusive world would likely be the biggest solar system discovery of the century. It would be a remarkable find. It would also be huge for our understanding of the solar system's origins and evolution, he added. Indeed, observing the planet could also teach us more about the formation and evolution of giant planets. This would not only help us learn more about planets in the solar system, but also shed light on thousands of giant exoplanets around distant stars. If space agencies like NASA send probes to fly close to the planet, they could also reveal more clues about the solar system's past. It'll have many secrets that will be unlocked by studying it in detail. How could humans make the trip to Planet 9? But if space agencies like NASA want to send a probe to visit the distant world, they first will have to plan and get approval for such a mission. And this, according to Andreas Hein, a space systems engineer at the University of Luxembourg, will take at least a decade or more. This is mostly because missions have to go through a lengthy and rigorous government selection process, he added. But this process could be sped up depending on how odd the world appears in initial readings. As Manasvi Lingam, a theoretical astrobiologist at the Florida Institute of Technology, said, if Planet 9 is anomalous in some respect, there could be more interest in expediting such a mission. It is also possible that a private space exploration company, such as SpaceX, could launch missions sooner, potentially as soon as 5 years after discovery, because they are not hindered by as much bureaucracy. How long would it take to reach Planet 9? And once a probe is sent to Planet 9, the next question is how long will it take to arrive? In 2022, Hein Lingam and part-time astronomer Adam Hibbard attempted to answer this question in a theoretical paper that was posted to the preprint database Archive. In this paper, which has not been peer-reviewed, the researchers estimated that it would likely take between 45 and 75 years for a spacecraft akin to NASA's Voyager probes to reach Planet 9. These calculations were based on the assumption that Planet 9 is around 400 astronomical units from the Sun on average, or 400 times farther away from the Sun than Earth. That's also around 13 times further away from the Sun than Neptune, the farthest known planet in the solar system. But subsequent studies suggest that Planet 9's true average distance from the Sun is actually closer to 500 astronomical units. And the most recent survey, which narrowed down the elusive world's potential hiding place, also hints that the planet could currently be more than 550 astronomical units away, near its farthest point from the Sun. However, these developments don't dramatically alter the timeline laid out in the 2022 paper. Because after all, the team's estimates were conservative, meaning that the upper end of their uncertainty range still seems tenable. On the other hand, Although 75 years may seem like a long time for a one-way trip, this is quite fast compared to the journeys of existing probes. For example, Voyager 1, the most distant spacecraft from Earth, has been traveling through space for 46 years and is only around 163 astronomical units from Earth. As a result, a Planet 9 probe would have to travel around 3 times faster than Voyager 1 to reach Planet 9 in the researchers' time frame. This may seem unlikely, but it is possible. Probes traveling toward the outer solar system must be gravitationally slingshotted around the Sun, planets, and their moons to propel them across the vast distances involved. Voyager 1's trajectory was carefully planned to allow it to fly closely past Jupiter, Saturn, Uranus, and Neptune, as well as some of their respective moons. To do so, Voyager 1 had to also be slingshotted around objects to slow it down and redirect it to where it needed to go. However, a Planet 9 probe could go as directly as possible straight to the mysterious planet, allowing it to pick up more speed and travel much further in the same amount of time. Mike Brown, an astronomer at Caltech who co-proposed the Planet 9 hypothesis in 2016, originally estimated that a probe could potentially get to Planet 9 in as few as 20 years using a similar method. But it obviously is too difficult to see how a probe could get to Planet 9 this fast using current technology. But it might be possible to reach Planet 9 quicker if we could crack more advanced propulsion technologies, such as light sails, giant sails that catch sunlight or lasers to accelerate spacecraft. The researchers suggested previously that a light sail could take as little as 7 years to reach Planet 9. However, it could take at least 20 years for light sails to become a reality, the team estimated. Thus, if we found Planet 9 tomorrow, it would be better to send a current probe than to wait for alternative technologies to become available. In short, as propulsion systems advance further, it may also be possible to send people to Planet 9, but probably not anytime soon. After all, as you see, our own planet represents a tiny fraction of the peculiar phenomena that can be found lurking throughout the cosmos, and every day astronomers turn up new surprises. Here are some of the most outlandish objects in space. 1. The Red Rectangle Nebula. Throughout the galaxy, gas clouds take on weird and wonderful forms, but one nebula in particular is baffling astronomers with its oddly geometric shape. Located in the constellation of Monoceros, the unicorn, the Red Rectangle Nebula sits 2,300 light-years away. Its distinctive shape could be due to the fact that 2 stars sit at its heart. If shockwaves from both stars hit a dusty ring surrounding the pair, they could create 2 cones of bright dust. Seen together, these 2 cones look like a square. To add to the mystery, the nebula also exhibits a rare phenomenon called extended red emission, where its dust glows eerily red. It isn't known exactly what causes this, but some researchers argue that it's due to intense ultraviolet light from the stars interacting with carbon-rich molecules in the dust. 2. Galaxy X. Astronomers are good at finding new objects by spotting their effects on their more conspicuous neighbors. Neptune was discovered thanks to its influence on Uranus. Black holes show themselves by the stars they bind into orbits around them. So when astronomers saw odd ripples in the disk of the Milky Way in 2009, thoughts naturally turned to some unseen disruptor. In 2015, they found the culprit: a dark dwarf galaxy orbiting the Milky Way, subtly altering the motion of our galaxy with its gravitational pull. We can only see this galaxy thanks to 4 bright stars that shine out of the gloom. Otherwise, the galaxy lurks in the shadows. To be this hard to see, Galaxy X must be largely made of dark matter, the invisible glue that binds galaxies together. In normal galaxies, this dark matter is peppered with visible stars and hot gas strung out like Christmas lights. But in Galaxy X, it's as if all the lights have gone out. In 2016, a Milky Way-sized galaxy, known as Dragonfly 44, was found to be made of 99.99% dark matter. It joined Segue 1, a dwarf galaxy discovered in 2006 that subsequent observations showed contains 1,000 times more dark matter than ordinary matter. That compares to a ratio of around 20 to 1 in our own Milky Way. Little is known of the origins of these ghostly galaxies, but studying them may help us to understand what dark matter itself is made of. 3. Elst Pizarro. Normally, it's easy to tell asteroids and comets apart. Asteroids are solid lumps of rock and metal, capable of careering into planets and killing dinosaurs. You typically find them in the inner solar system, particularly in the asteroid belt between Mars and Jupiter. On the other hand, comets are icy bodies that form on the outskirts of the solar system. On their rare forays towards the sun, their frozen bodies react with solar radiation to create spectacular tails. However, an object known as Elst Pizarro refuses to be so neatly pigeonholed. When it was first discovered in 1979, its orbit in the asteroid belt led to it being classified as an asteroid. But when it was examined more closely in 1996, it showed itself to have a tail, like a comet. Astronomers first thought that the tail was debris from a collision, rather than something bestowed by the sun's heat. But the tail's brightness and structure changed over time, pointing to an ongoing process rather than a one-off event. The object's rapid rotation, completing a full spin in just 3.5 hours, also said comet. However, one possibility is that a collision has exposed some subsurface ice on the body, which is slowly being lost to space. In this case, Elst Pizarro would be an asteroid masquerading as a comet until it has shed all of its exposed ice and gone back to being a standard asteroid again. Arguments still rage between astronomers. To settle them once and for all, space scientists had hoped to launch the Castalia spacecraft for a closer look in 2028. However, the mission failed to get the green light in the European Space Agency's 2016 round of funding, so the disagreements continue, for now at least. 4. Tabby's star. Oumuamua isn't the only object that has got people talking about alien technology. Extraterrestrials have also been implicated in the mysterious dimming of Tabby's star. Located nearly 1/500 light-years from Earth in the constellation Cygnus, it is named after the astronomer Tabitha Boyajian. She was the lead author of a 2015 study which showed that the star occasionally rapidly drops in brightness by a whopping 22%. The star's overall brightness has also been seen to fade more slowly over several decades. The short-term variation was picked up by the Kepler Space Telescope, whose job it was to find alien planets by analyzing the light of distant stars, looking for dips in their starlight as a planet passed in front of them. However, unlike the dimming of Tabby's star, the dimming caused by planets is evenly spaced. As it happens each time the alien world completes an orbit and is also relatively small, normally under 1%. That, as astrophysicist Dr. Eva Bodman at Arizona State University said, makes Tabby's star just keeps getting weirder and weirder. So what else could be dimming the star? One idea is that a swarm of comets is plunging into the inner regions of the star's solar system, producing huge amounts of dust in the process. It's this unevenly distributed dust that might be preventing some of the star's light from reaching us, causing the rapid brightness changes. But that wouldn't explain the other pattern of long-term dimming over decades. Comet dust dissipates in just a few months. This has led others to claim that the culprit might be megastructures built by advanced aliens to harvest the star's energy. If this technology was unevenly distributed around the star, it would cause sporadic dips as it orbited, and it would also block more light over time as the project was constructed, explaining the longer-term fading. But this is a notion that Bodman rejects. She points to observations of the rapid dimming that show more light is blocked at the blue end of the spectrum than the red end. Blue light has a shorter wavelength, so this is exactly what you'd expect if it was being scattered by small dust grains. However, analysis of the light spectrum linked to the longer-term dimming implicates larger dust grains. Therefore, we might be looking at a complex cloud of different-sized dust grains blocking varying amounts of light as its orientation changes over time. Regardless, the source of all that dust still remains a mystery. The long-term variations of Tabby's star can be traced back to at least the 1890s. Dust shouldn't persist over such timescales, so it seems that some process is replenishing the dust as it's transported away by the outward pressure of the star's light. In short, there's no obvious explanation for what's going on. 5. FRB 121 Note 2. Of all the things leaving astronomers scratching their heads, fast radio bursts, or FRBs, are particularly vexing. As their name suggests, they are sudden, rapid chirps of radio waves, often lasting mere milliseconds. The first one was picked up by our radio telescopes in 2007, and we've been scrambling to try and explain them ever since. These FRBs appear to be coming from outside the Milky Way, often hundreds of millions of light-years away. To be seen from such a distance, they must release as much energy in a fraction of a second as the Sun does in 80 years. Explanations range from colliding black holes to signals from extraterrestrial civilizations. But before astronomers had managed to figure them out, the universe threw us another curveball. A burst known as FRB 112, emanating from a small galaxy 3 billion light-years away, was seen to repeat. On just one day in August 2017, it repeated a staggering 93 times, ruling out a single event as its cause. Whatever triggered the burst had to be ongoing. So maybe FRBs are caused by rapidly rotating neutron stars, or material continuously falling into black holes. Of course, FRB 12112 could be a red herring. There could be two separate causes of repeating and non-repeating FRBs. In October 2018, a new haul of 19 non-repeating FRBs was announced, including the closest and the brightest FRBs detected to date. Studying their properties should help us to pin down their home galaxies, and ultimately, we hope, the cataclysmic processes that are causing them. 6. Hoag's object. We live in a flat spiral galaxy known as the Milky Way. Other galaxies, called ellipticals, are shaped like rugby balls. But Hoag's object appears to be neither. It has an older yellow core surrounded by an outer ring of young blue stars. But in the middle, nothing. It's like something has swept away the spirals. There's no other galaxy in the universe quite like it, and astronomers are stumped as to how it formed. It was spotted in 1950 by American astronomer Arthur Hoag, and perhaps the most feasible explanation offered so far is that 2 to 3 billion years ago, a small galaxy sped through the larger disk-shaped galaxy, creating this unusual structure. But there's no sign of any galaxies nearby that might have served as the bullet, and such a collision would have sped up the core of Hoag's object, whereas observations show that it spins slowly. To add to the conundrum, if you look closely at roughly the 1 o'clock position, there's a smaller version of the galaxy hidden within itself. 7. The Bermuda Triangle of space. Imagine drifting off to sleep when, still with your eyes closed, you're suddenly startled by an intense flash of light. This is exactly what some astronauts have reported when passing through the South Atlantic Anomaly, or SAA, a region of the Earth's magnetic field also known as space's Bermuda Triangle. Scientists believe it is linked to the Van Allen radiation belts, two rings of charged particles trapped in our planet's magnetic grasp. Our magnetic field is not perfectly aligned to the rotation axis of the Earth, which means these Van Allen belts are tilted. This leads to an area 200 kilometers above the South Atlantic where these radiation belts come closest to the Earth's surface. When the International Space Station passes through this area, computers can stop working, and astronauts experience cosmic flashes, probably due to the radiation stimulating their retinas. Meanwhile, the Hubble Space Telescope is unable to take observations. Further study of the SAA will be crucial for the future of commercial space travel. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.